Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature.
Dear students, in this video, we are going to study about Young's double slit experiment to produce equally spaced interference fringes having bright and dark bands. We also study about the expression for bandwidth.
We usually think of light as a simple addition problem. If you shine a flashlight on a wall and then shine a second one on the exact same spot, that spot gets brighter. But if you set those light waves up in a very specific way, adding a second beam of light can actually cause the spot to go dark. To see this happen, you need coherent light. You can't just use two different light bulbs, because the waves they emit are a chaotic mix of phases and frequencies that will never properly sync up. Instead, physicists use a technique called wavefront division. They take a single wave from a single source and split it. This guarantees that the resulting waves have the same frequency and start in sync. To make light cancel light, we don't combine random beams. We take one wave, divide it against itself, and force those divided parts to overlap. The most famous demonstration of this is Thomas Young's double slit experiment. This photograph shows wave behavior. A single wave hitting a two-slit barrier creates identical, simultaneous sets of circular ripples propagating outward. Because these waves occupy the same space, they overlap. Every wave has high points, or crests, and low points, or troughs. As these two sets of waves spread out, those crests and troughs intersect. Where the crest of one wave meets the crest of another, they amplify each other to form a bright spot. Where a crest meets a trough, they cancel each other out entirely, leaving a dark spot. Right in the middle of the screen, the waves from both slits travel the exact same distance. They arrive in phase, crest to crest, creating a strong central bright fringe. The physical overlapping of these identical waves creates an alternating pattern of light and dark fringes across the viewing surface. Knowing that light and dark bands exist is only the first step. To predict exactly where any specific fringe will appear on the wall, we have to translate this physical wave behavior into abstract 2D geometry. This diagram shows the setup using core dimensions. We have two slits, S1 and S2, separated by a distance we'll call lowercase d. Far away, we place a screen at a distance capital D. Let's pick a point on that screen, point P, located at a height y from the center. Light travels from slit 1 to point P and from slit 2 to point P. Because P is above the center, the bottom ray has to travel a slightly longer route than the top ray. We call this extra length the path difference, represented by the Greek letter delta. Whether point P is bright or dark depends on how delta compares to the wave's length. If the extra distance is exactly one wavelength, the waves arrive crest to crest and reinforce each other. But if the distance shifts by half a wavelength, the crest of one wave meets the trough of the other, canceling the light into a dark spot. We can find delta by looking at the geometry near the slits. We have a right triangle here. Using basic trigonometry, the sine of angle theta equals the opposite side, delta, divided by the hypotenuse, lowercase d. Now we look at the triangle spanning the room. For this one, the tangent of angle theta equals the opposite side, height y, divided by the adjacent side, distance capital D. In reality, the screen is often meters away, while the slits are fractions of a millimeter apart. That means the angle theta is very small. This scale disparity lets us use a mathematical shortcut. At tiny angles, the sine of theta and the tangent of theta are virtually identical. Because they are effectively the same, we can set our two equations equal to each other. Delta over lowercase d equals y over capital D. Multiplying both sides by d gives us delta equals d times y divided by capital D. By exploiting the difference in scale, we built a geometric formula linking the microscopic path difference to the macroscopic screen position. We can now combine the wave condition for a bright fringe, where the path difference delta equals an integer multiple of the wavelength, with our geometric formula. Take a moment here. Substitute n lambda into the geometric equation and algebraically solve for y to find the exact position of any bright fringe. To locate the bright fringes, we replace delta with n lambda. We isolate the height y sub n by multiplying both sides by capital D and dividing by lowercase d. The position of the nth bright fringe is n times lambda times capital D, all divided by lowercase d. We apply the same logic for destructive interference. Substituting the half-integer rule for dark fringes into our geometric equation gives us the position formula for any dark fringe. We can now pinpoint any fringe on the screen using only the wavelength of light and the physical dimensions of the experiment. Young's double slit experiment takes a microscopic physical wave property, interference, and magnifies it across a room, giving us a macroscopic geometric pattern we can measure on a wall.
Now let us study about Young's double slit experiment. This experimental setup is as follows. Thomas Young, a British physicist, in 1801 used an opaque screen with two small openings called double slits, S1 and S2, which are kept equidistant from a source S, as shown in the figure. The width of each slit is about only 0.03 millimeter, and they are separated by a distance of about 0.3 millimeter only. As S1 and S2 are equidistant from S, the same wavefront is cut by S1 and S2. The light waves at S1 and S2 are said to be in phase with each other. So S1 and S2 act as coherent sources, which is the requirement for obtaining interference pattern. So this is the experimental setup, in which there is a double slit. There is one source S, and light from this source S will pass through two slits S1 and S2, and they will produce an interference pattern on the screen, which is kept at a distance d. Here the wavefronts from S1 and S2 spread out and overlap on the other side of the double slit. When a screen is placed at a distance of about 1 meter from the slits, alternate bright and dark fringes, which are equally spaced, appear on the screen. We should remember that the fringes will be equally spaced in the case of interference pattern, whereas in the case of diffraction pattern it will not be so. So these are called as interference fringes or bands. So that's the way of identifying an interference pattern and the diffraction pattern. The intensity will be also uniform in the case of interference pattern, and the intensity will be decreasing from the center in the case of the diffraction pattern. And using an eyepiece, the fringes can be seen directly. At the center point O on the screen, the waves from S1 and S2 travel equal distances and arrive in phase, as shown. These two waves constructively interfere, and a bright fringe will be observed at O, and that is called as central bright fringe. When one of the slits is closed, the fringes disappear and there is uniform illumination on the screen, and this clearly shows that the bands are due to interference only. Now let us arrive at the equation for path difference. The schematic diagram of the experimental setup is as shown, and let d be the distance between the double slits S1 and S2. So here this small d is the distance, and these two slits S1 and S2 will be acting as coherent sources of wavelength lambda. The screen will be placed parallel to the double slit at a distance d from it. The midpoint of S and S2 is C, and the midpoint of the screen O is equidistant from S1 and S2. P is any point at a distance y from the center O, so this is the point P, which is at a distance y from the center O. The waves from S1 and S2 meet at point P. They will be either in phase or out of phase depending upon the path difference between the two waves. So the path difference delta between the light waves from S1 and S2 to the point P is given by this expression delta equal to S2P minus S1P. And a perpendicular will be drawn here from the point S1 to the line S2P at EM to find the path difference more precisely. That's given by delta equal to S2P minus MP, that's equal to S2M. Now the angular position of the point P from C is given by theta, and so the measure of angle OCP is given by theta, and from the geometry the angles measure of angle OCP and measure of angle S2 S1M will be equal. That means this measure of angle OCP will be equal to theta, and in right angle triangle S1 S2M the part difference is given by S2M equal to d sin theta. Therefore the part difference delta is given by d sin theta. Now if the angle theta is small, sin theta can be written as tan theta, and that will be equal to theta 1. From the right angle triangle delta OCP, tan theta is given by y by d. The part difference is given by the expression delta equal to dy by d. Here this small d is the distance between the two slits S1 and S2, and capital D is the distance of the screen from these two slits. Now based on the condition of the part difference, the point P may have a bright fringe or a dark fringe. Now let us see what will be the conditions for obtaining bright fringe, that is called as maximum. The condition for the point P to have a constructive interference or be a bright fringe is given by this expression part difference delta equal to n lambda, which means an integral multiples of the wavelength. So n can have 0, 1, 2 values. That means dy by d will be equal to n lambda, or y is given by n lambda d by d. And for any nth bright fringe, yn can be written as n lambda d by d. So that's the condition for the point P to appear bright. So the distance yn is the distance of the nth bright fringe from the point O. Now let us see the condition for dark fringe or minimum. The condition for the point P to have a destructive interference or be a dark fringe is given by this expression for part difference delta, that's given by 2n minus 1 lambda by 2. So here n is an integer, and that is also equal to 1, 2, 3, etc. Therefore dy by d equal to 2n minus 1 lambda by 2, or that will be separated by a distance y equal to 2n minus 1 lambda d by d here by 2. So we can write this expression for the nth dark fringe as yn equal to 2n minus 1 by 2 into lambda d by d. So there is a condition for the point P to be a dark fringe. So the distance yn is the distance of the nth dark fringe from the point O. The formation of bright and dark fringes is as shown in this diagram. So if you have a constructive interference, the point P will appear as bright. That means here the wavelength will be separated by a distance lambda, these two ways. Whereas here in this case there will be a destructive interference which will lead to a dark fringe. So this shows that on the screen alternate bright and dark fringes are seen on either side of the center bright fringe. The center bright fringe is referred as zeroth bright fringe, followed by first dark and first bright, and then second dark and second bright, and so on either side of O successively as shown here. So this is the interference fringe pattern like this you have. Now let us arrive at the equation for the bandwidth. Now let us see what is the bandwidth of the fringes. The bandwidth, that is denoted by letter beta, and that is defined as the distance between any two consecutive bright or dark fringes. The distance between n plus 1th and the nth consecutive bright fringes from O is given by this expression beta equal to yn plus 1 minus yn, that's equal to n plus 1 lambda d by d minus n lambda d by d. And so for the bright fringes, the bandwidth is given by beta equal to lambda d by d. Similarly, the distance between n plus 1 and the nth consecutive dark fringes from point O is given by this expression beta equal to yn plus 1 minus yn, that's equal to 2n plus 1 minus 1 by 2 into lambda d by d minus of 2n minus 1 by 2 lambda d by d. So for dark fringes, the bandwidth is given by the expression beta equal to lambda d by d. And so from these two equations, we understand that the bright and dark fringes are of same width, equally spaced on either side of the center bright fringe. Now let us see what are the conditions for obtaining clear and broad interference fringes. First point, the distance d between the screen and the double slit should be as large as possible. That's about 1 meter. And the wavelength lambda of light used must be as long as possible. then the next case, the distance d between the two slits must be as small as possible. So these are the conditions for obtaining clear and broad interference fringes.